We Ayush Prasad back for another episode of the Funtastic Academy. In the last video about why objects are colored, I gave you a simple quiz question. What color of light has the shortest wavelength? What could that be? The answer is purple. Although technically there's no answer because light can have as low a wavelength as you want. But when it comes to visible light, the only contender that's even contending is purple. Okay, so with the quiz question out of the way, we can now talk about this video's titular topic, the speed of light. Okay, so Jupiter has a moon called Io, and Io has eclipses, and scientists know when those eclipses are going to happen. But a guy named Ole Roma noticed something. He noticed that the predictions happened a few minutes before the actual eclipse of Io. And this lag time would change over the few months. Okay, so what did he conclude? He concluded that light was taking time to come from Io to Earth. And because the distance from Io to Earth was keep on changing, the lag time also kept on changing. Okay, but that just proved that light had a finite speed. It didn't exactly say what that finite speed was. To measure that, we would need the help of a scientist named Chizo. Chizo had a simple setup. A lantern. In front of the lantern was a gear. In front of the gear was a mirror. And he rotated the gear super duper fast. And he waited to see if the light would come bouncing off the mirror. Because if it didn't, then that means the gear was rotating too fast. But if it did, then that means the gear was rotating slow enough. And using super complicated math I definitely understand but don't have time to talk about, he figured out exactly the speed of light. But something weird happened. The speed of light in air is faster than the speed of light in water. How could that be? Well, it's basically because the light is gonna bounce off all the particles. In air, there are much fewer particles to bounce off of than water. So light is slowed down in water much more than it is in air. But what are the effects of this material speed changing of light? Well, one of the most important effects of this is refraction. But what is refraction? Well, to understand that, let's do a very simple demo experiment. Refraction. Such a complicated word, but so simple to understand with just a simple demo experiment. Okay, so you have 5 seconds to tell me how many coins you see. Did you say 1? That's correct. Okay, now let's play the same game again. Did you say 2? If you did, you're both wrong and right at the same time. That's because even though it looks like 2 coins, there's actually only 1 coin. Okay, but how in the world does this work? I mean, how can the coin change the amount of coins they are simply by dunking it in water? Obviously, it's not magic. It's science. Okay, but what exactly is the science behind it? Let's understand when we talk more about refraction. Oh, you're here. Okay, so let's talk more about refraction. Okay, so as I mentioned earlier, the speed of light is different in different materials. And 300 years ago, a guy named Fermat proved that light always likes to take the shortest path between point A and point B. Okay, so that was a very simple statement, but if the light is passing through materials at different speeds, then that would mean that the light would have to change paths as it passes from one material to another. In other words, light is going to bend. The measurement for how much this light bends is called index of refraction, or I. I equals C. So C is the speed of light in a vacuum. A vacuum is a place where nothing is there, like space. Okay? I is equal to C divided by V. V is the speed of light in the material you're talking about. So air is very less dense, so its index of refraction is almost 1. Water is more dense. The index of refraction is slightly higher, at about 1.3. Okay, so how does this index of refraction explain our double coin? Let's draw a diagram. This is the container, this is the water, this is the coin. Okay, so let's imagine that light hits this coin and that produces an image of the coin. But this image has to escape from this container and into your eye, which I'm going to place right here. There are 2 paths for it to escape. One, it goes here, and in that case it refracts. In other words, it bends, like so. Or it goes like this. That means it refracts or bends like so. But oh look! There are 2 different images of the coin at different places. And your eye interprets these as 2 different coins. So that's why we saw 2 different coins. Another context where index of refraction can be useful is in glasses. Have you ever wondered why glasses have to be made out of glass? Because if they were made out of diamonds, they would be diamonders. Okay, that was a horrible joke, but still, why do glasses have to be made out of glass? Why not diamond? It's simple. Glass has a lower index of refraction than diamond. Remember what we said about the index of refraction? It's nothing but a measure of how much light bends in that substance. So that means light bends more in a substance like diamond than it does in a substance like glass. And that would create a blurry image. So if you were as rich as Bezos and ordered your workers to make a diamond glass, you would be wanting your money back because they would work horribly. And on that note, let me leave you with a quiz question. What is the formula for index of refraction, and what's the index of refraction for water? I'll give you the answer in the next episode of the Funtastic Academy.